Greetings, my friends. Today I want to number all tuples. What are tuples? Tuples are basically ordered sets of numbers, kind of like vectors, right? Well, tuples are generally used with integers only, and we are gonna use only non-negative integers, so natural numbers and zero. Yeah. Okay, so what do I mean by numbering? Well, I wanna give uh, every tuple its own natural number. So I want to build something that's called a bijection. Bijection means like there's one-to-one correspondence between each tuple, a collection of numbers, non-negative integers, and some natural number. Sounds like something doable, right? Countably infinite on both sides. Well, we'll see. We'll see. Um, well, of course, there can be different ways of doing this. I want to talk about mainly Cantor's way. You know, Georg Cantor, a very smart German dude who came up with his own numbering system. So first of all, let's start from the beginning. The smallest tuples we can have are tuples of size 1, length 1. Well, it's quite trivial and easy to number them, of course. Might have a guess? Well, the number of tuple of length 1, we're gonna call it C1 of tuple x, for example, is gonna just equal x. For example, we have a tuple 2, it's gonna have a length 2. Alright, sounds simple enough. Now we have to number the tuples of length 2. Okay, let's look at this. I'm gonna make a list. I'm gonna make a list of all tuples of length 2, and I'm gonna do it like this. We're gonna start with all the tuples where the sum of both the integers is 0. Then we're gonna list all of those that have the sum 1 and 2, and you can see I have this sort of system where I start with the tuple of that looks like 0n, right? And then I list them all in this sort of order. It's not the single possible kind of list, but I want to use this one. And of course, if we have a list, we can assign a number to each of the entries in that list. I'm gonna use this sort of way with the arrows, and I can list all of these numbers starting from zero. Yeah, because we use non-negative integers, so naturals plus 0. I'm gonna use the number also being naturals plus 0, so I'm gonna start with 0. Sounds kind of probably right, because 0 comma 0 is gonna have a number 0. I don't know, it seems kind of natural to me. So of course here we can see that, for example, the tuple of that looks like 2 comma 0 is has the number 5, and 2 comma 1 has the number 8. We can look at this sort of numbering a little longer, and we can derive a formula. I can say that triangular numbers come into play here. Triangular numbers are these sorts of numbers that look like the sum of first n natural numbers. They are 0, 1, 3, 6, 10, 15, 21, 28, and so on. And here the number of tuple 0n is the nth triangular number. And then, of course, if we have a tuple that looks like xy, the sum of those two numbers gives us the row, right, of this list, and x in particular gives us the place in that row. So we can use the formula where the first part of that formula tells us the particular triangular number, and then we add x to get the particular number for this tuple. Alright, sounds good. So, have we solved our problem? Well, not quite. Alright, I only have numbers for tuples of length 1 and 2, but I want to go further, right? Well, there is a way to go further. Uh, and I'm gonna make it sort of iteratively or recursively, maybe even, right? Um, I want to find the number of the tuple of length 3. I'm gonna say it's just a tuple of length 2, where the first two elements are put together into their own little tuple. And in general, I can make this description where I define a tuple of length n, its number as the number of tuple length n minus 1, where I put two first elements together. So we can see here that Cn of x1, x2, and so on xn is equal to Cn minus 1 of C2, x1, x2, and so on xn. Alright, so have we solved our problem? Well, not quite yet. Not quite yet. As you can see, we only have numbering systems for every sort of length of the particular tuple. But you can see that two tuples of different lengths can have the same number. It's very obvious. So what can we do? And this is where Cantor had a very great move. He creates something that's known as a Cantor's numbering for each tuple. He basically defined the Cantor's numbering for each tuple. It doesn't have an index, and we write it as A for x1 and so on xn as the C2 of a particular tuple, the tuple which has the number of that tuple of its length and its length minus 1. So here we pair each tuple with a different tuple of length 2 and we find its number. And it could be proven, or maybe it's obvious to you if you're very smart, that this also is a bijection and actually gives us the number for every tuple. I think it's quite an interesting exercise to look at the structure of this numbering. So of course a tuple with big numbers has a big Cantor's number, but also a tuple with a lot of numbers also has a Cantor's number quite large. So here we can see that this this problem is actually solvable. I think it's quite a cute little theorem from this area of mathematics, and if you're interested more, I can recommend you looking at the structure of this numbering, and also you can solve the problem in reverse, where you have the number and you want to find its tuple. I think this is actually quite difficult. It's a lot more difficult, but we only described the first problem here. Well, I thank you for your attention.